All right. Welcome to this second day keynote. I'm happy you made it. It's 9 a.m. It's kind of early, especially for those who partied yesterday. My name is Stephane Maldini, and I'm a co-founder of a project named Reactor, which I lead now. And we started a collaboration with the Spring Framework team last year, including with Rossen.
Hi, my name is Rossen Stoyanchev, and I work on the Spring Framework team. Indeed, about a year and a half, we started investigating options for building web applications in a different way, that scale in a different way, and that are fully non-blocking. And the result of this collaboration is a Reactor 2.5 release. A set of releases. We're in milestone phases at the moment. And also, Spring Framework 5, milestone 1 is just around the corner. It's coming up. So we are here today to share some of our experience, why we started on this journey. And you may be wondering why we've spent so much time investing in this area. So we want to explain some of that.
So the investment we make in reactive architecture, and we have time to go through on this presentation why we do that, and you will probably get it hopefully after the presentation, but why Pivotal is interested into reactive architectures or reactive in general. Well, you know, reactive as a quality defined as saving resources, and Pivotal makes its own business on selling instances on Cloud Foundry. So you could argue like, why is that important to Pivotal to make efforts to save resources if we sell more instances? Well, it's not really that question that is interesting for Pivotal. We'd like our customer to deploy more microservices in the end, and you know, anyone who's buying Cloud Foundry is sticking to its budget anyway. So the point is, with efficient resource saving, as promised by reactive architecture, we plan to offer you to deploy more microservices in the same predefined capacity model. So that's very important to us, not to leave you with a set of resources you can really use at its maximum potential because your application doesn't scale or is not efficient for the cloud. And that's the answer we try to provide to Pivotal.
So if we could have a time machine and a time clock and go back 20 years to the early days of Java, that was also the early days of the internet. And in the early days of the internet, if you remember, the way that we used to run applications was through CGI. And this is something that would be completely unimaginable today, to spawn a new process for every request that's coming in. And clearly, we've come a very long way since those days. But it was in this context 20 years ago, or a little bit less than 20 years ago, that the Java Servlet API was born, with the Servlet 1.0 specification completing in 1997. And the original vision for Servlet API, the way that it was conceived, is that we would take advantage of the concurrency on the JVM, and the Servlet container would maintain a thread pool and then allocate a thread for each incoming request, which meant a relatively straightforward, simple concurrency model where individual requests and servlets, as they process requests, they don't need to worry about concurrency. They don't need to worry about overlapping with the other requests coming in. And the servlet container would basically take care of the concurrency. So this was the model we actually accepted, and this was relative to what was happening in the day with CGI. And obviously, I mean, that made a lot of sense, the way that it took place. And we accepted that as the model that we use today. Now, in the meantime, we went on to solve many other problems that kept our attention for many, many years. We wrote web frameworks, we invented Ajax, then we dealt with Ajax. Then we went through the whole REST versus SOAP debate, Flash and Flex, single-page applications. There's so much that's been happening in the web that has kept us busy. But in all this time, this same processing model that we have hasn't really changed. Now, to be sure, the underlying servlet containers, the Tomcat, JD, have really changed tremendously over the years. I mean, there's probably almost nothing that comes from the early days. And they've improved with the times, and they continue to innovate at great pace. But the underlying servlet processing model that we have still from back then continues to be the case today. So given this processing model, it defines the way that we scale applications. It kind of frames the context in which we work, and that's where Stephane will talk about how it is that we scale today.
So, well, I guess you recognize the picture behind me. A server container is something you do use now as a norm day to day. We see more and more development on some other runtimes. But right now, classic way to scale or classic way to deploy applications is to use a servlet container. And one of the defining traits of servlet container is the thread pool they have. Because the model is a thread per request, you need to have a large thread pool to handle a large volume of requests. Request per thread, so a lot of thread available for requests. The issue in that being, well, there are multiple issues in that. The one we can find quickly is the fact that there is, in your application, no matter what you're doing, a kind of processing latency. So you can access a backend database, you can do something that takes time or not, but you have to do something during the time the request is here. That means this processing latency is going to impact the response time anyway. No matter what you do, we have to reply at some point. And another issue comes in, which is the network latency. And the network latency coming from the request, as you see on the left in the diagram, they can come from various clients, slow, fast clients, and we don't control actually how fast they're going to connect to your application. Some are going to use 2G, 3G networks. Some are going to use broadband. So the latency is going to be unequal between different requests. So what can go wrong with this model? So the application processing itself is going to take some time, although it doesn't prevent, to have a thread pool, for instance, and that happens a lot. If you use Spring, you will use, for instance, the task executor, and you will fire off different thread events just to process your thing. But in the end, you will reply something to your clients, to the connected HTTP request. So meantime, something is processed, a request is processed by your application logic. What can go wrong is, if this application logic really takes time, and sometimes random time, especially in the context of today where we access remote resources like backend, HTTP backend in the context of microservices, or just a backend database. So these connections will take time anyway. And because they take time, they suffer the same issue you suffer on the other side with the request. They will have network latency, which is completely different from a request to another one. And if you take that in account, that means, because you keep receiving requests, and that means, what does it mean actually? If you keep receiving requests and the processing of the request is slower than the acceptance of new requests, well, it's normally not rocket science what's going to happen. At some point, you fill the backlogs of the different thread pool or processing pool you use. And when you I'm going a bit fast. When you when you reach the maximum backlog of these processing queues, what happens for your incoming request, the incoming clients? Well, they can't connect anymore. Because remember, it's a thread per request, and if all the threads are busy and you can't submit any more tasks, what happens in that case is, well, the application becomes unresponsive. And I'm pretty sure everyone has seen that at some point.
No.
Yeah. So what do you do at this stage? You know, your application is a bit stuck. What's the classic way to solve that we do? Well, we tend to defer the issue by finding other way. If this application is actually stuck, let's deploy another application, and let's put a load balancer in front of it. Classic way of scaling. What can go wrong then? You know, you can still add more instances. Well, what can go wrong is if your application actually is becoming unresponsive, for instance, because it's full, the backlog, remember, is full, so it doesn't accept more connections. Well, even the load balancer has some mechanism to check if the application is alive. It will connect, ping, and say, are you dead, are you dead? And at some point, because the application is overloaded, it will consider maybe the application dead. Eventually, even the application can catch up later, but for now, it's going to remove it from the different routes it can route to. And when we arrive to that stage, we dezoom a bit, and I think you kind of see the issue where the point where I'm going to, the domino effect we have because the application itself is not designed to accept a certain volume of requests because of the difference between the processing time and the volume of request. This cascades into infrastructure issue. I mean, if you need to deploy new copies of your application to scale, at some point you will need to think about, well, how you deploy this application. Are you going to use a container? Are you going to use a VM? Are you going to use a different physical host machine? So usually, especially in nowadays with the microservice architecture, people tend to advise or tend to advertise this way of scaling where you have pool resources in the cloud, host one, physical host, and your application are going to reuse these resources. So if, for instance, in that case, I would like to scale out more application B, for instance, I will just deploy another application B in the second physical host. And that's cool because I reuse the second physical host resources. And that's also what we call elastic scaling. You can deploy on demand if you need more resources, more application B, because one of these application B is dead, or you want to scale for a peak load. You can even deploy on the same physical machine two times the same application. That's a classic way of scaling, when you have mutualized resources. And that's what we advertise with cloud in particular. And because it's elastic, the cool thing is you can also undeploy after peak load to save some resources and maybe deploy something else. But that's what we expect or we'd like to happen. The problem is, remember, the backlog is filling up if your processing latency is slower than the incoming request traffic. So usually, with a filled backlog, the application 1 or A is, in that case, is actually consuming a chunk of resources not expected. You don't control actually the resources it actually uses. So if you want in reality to deploy an application and scale it because it's not that resource efficient, the classic way of scaling nowadays often comes down to adding a physical host because that's the only way to cope with the inefficiency of the application. Or to scale out for more requests. And that has a cost, actually. I guess it's not only a cost in terms of money. Buying a new hardware is like a process as well. And I'm pretty sure if you work in large companies, you've seen this kind of process taking time, sometimes months. I've seen sometimes for just scaling out a process of 6 months in some banks or a large telecom company. And that is too much. In nowadays, we want to scale quickly. It's Christmas. We want to make sure that we have enough capacity to accept all these requests. And then we want to unscale because it's costly. Plus, it's not elastic, really. A process of 6 months versus deploying automatically new application on an already available resource you want to reuse is always going to be faster than ordering a new, purchasing a new host, for instance. So the question is, will actually that need you to think about it, because it's not only about the money, but what else can you qualify as a driver to say, okay, should I really be interested into what these two guys are saying?
So when we cover this topic, when we speak on this subject, very frequently the most natural question, one of the first questions is, do I need to change? Does my application need to change? And it's really easy to fall into a way of categorizing this as old versus new, old generation versus new generation, or good versus bad. But it really, there isn't an easy answer to this question, and by falling into this way of thinking, it's actually making the answer even more difficult, the question even more difficult to answer. But really the way to think about this is as a kind of scale. On one side of the scale is the simplicity of building applications the way that we do it today. The blocking, as much as it sounds like a bad word, blocking and imperative way of writing applications is actually the simplest way to create and to write logic. And there's a reason why we've been using that for a long time, and that's going to continue to be perfectly appropriate for many categories of applications. So if anybody tells you otherwise, you could probably think about going the other way. But at the same time, on the other side of the scale, we have situations that involve latency, like the ones that Stephane was just talking about. The old servlet processing model that we adopted a long time ago, again, assumes that you have a thread per request, and then you use that thread, and you finish up pretty quickly. But the more you start to deal with latency and making calls to remote APIs, the more you get into situations where the simplicity is just beginning to fall apart because you're dealing with asynchronicity anyway. You're dealing with multiple threads because you have to make calls out, and at some point, if you choose to do it in a blocking way, well, that's going to slow you down to the point where scale begins to be affected. So that's the frame in which you want to think about this, and there is no easy answer for when or if you should change, but this is the kind of scale that we're talking about that you can use to reason about and to think. And of course, in the Spring Framework, we plan to maintain both of these approaches. We're not going to say this one is retired and this is the new way of doing things. They're going to be maintained side by side as first-class citizens, and it's going to be for you to decide which one is right for your situation. Now, over the past 10 to 15 years, also, things have changed tremendously. I mean, if you really go back 10 years or more and think about the mind frame in which we operated, it was completely different. First, the social media became mainstream, so large-scale internet websites, pretty commonplace, a lot of places dealing with technical issues that come along with that. You have our own expectations as users of the internet and its interconnectedness and its resilience and the amount of scale that it provides. It sets our expectations in subtle ways in what we expect from applications to do. And eventually, that you could say that feeds back onto the way we build applications today. So the whole thing with microservices, which is not anything new. We've been trying to do that for a long time. We also started deploying into cloud environments, and the large internet companies began to open source their internal stacks for us to use. And of course, microservice architecture basically means that latency is no longer the exception in the way that we do things. Latency is now pretty much the norm. And again, these are subtle changes. They don't necessarily affect every application that's out there. There are plenty of applications that are going to continue to be fine with the way they are. But this is now a completely different mind shift. It's a completely different context in which we operate, in which we think about what we aspire to in terms of architecture these days and what we're trying to do. So is there another way that we can do things?
Well, that's an interesting question. Of course, there is another way, otherwise we won't be speaking here. But there is another way, and you know, if you really think about this other way, after taking off, you know, to this other way, you would land on a new planet and you meet with new friends. So these ones are Rick and Morty from a show. Actually, I advise strongly watching it. And you know, you will meet with new friends like Netty, Node.js. These names sound familiar, and they are both, you know, non-blocking runtimes. And that's really where all things start, actually. these runtimes, they're used by very popular large, and they are deployed on large-scale architecture. Apple used Netty, for instance, for things like iCloud, and Netflix also used Netty. So this new runtime are also hardened by some very serious companies. But how does it work, actually? The defining trait of this runtime, I guess maybe some of you know that, but this non-blocking runtime have a specific trait. They don't use a lot of thread. And not using a lot of thread, so in that case, we have, for instance, 4 threads, 1 selector, and 3 workers. We also call them event loops. I guess you heard about this term as well. So what can go wrong with this model if you change your application to not deploy on a container, on a servlet container, and you start using a non-blocking runtime like Netty because it's on the JVM anyway? Why not using Netty? Well, the interesting fact with non-blocking runtimes is the decoupling we have in the model of connections. So now we can write the response back anytime. Remember, with the servlet container model, we had to reply at the end of the request. And you can change that. You can use whatever deferring mechanism, but at the end of the request, you have to reply. In that case, we have independent write and read notification, which is great because that means if someone is slower than someone else, you can actually, well, the Netty non-blocking runtime is going to still remain efficient. That's great if you have environment with different latency, because you're going to be notified when something is available for a read or for a write. So what can go wrong with this kind of non-blocking runtime? Well, they will suffer the same thing if you didn't change anything else, if you just use Netty and continue using your application the classic way, make calls to backend like a database, a remote HTTP service, or whatever. So there's still latency in the processing logic. The processing is still going to take time. But this time, remember, we only have a few threads. So usually, if you start blocking on your application, it's even worse than the situation you might end up with servlet container, because now you really block everything. In servlet container, when you block everything, you can still at least do something like closing the connection, writing the response as quick as you can. But in the case of Netty, if you start blocking, or Netty or Node.js or whatever, if you start blocking, actually the backlog of events from write, read, etc. is going to be blocked. So regardless of, even if you try to close or write something back to a connection and you're already processing the connection, you will be stuck. So it's a complete deadlock in that case. It's really worse than the servlet container if the application processing itself is blocking. So, well, if the application itself is blocking, can we do something about it? Do we need to change also the application stack? Well, there is another way to create application as well. And to work with this kind of runtime, you need to be non-blocking. And that's actually a requirement for this kind of system. If you really think about it, there is no way you can get away from non-blocking at the application logic. Otherwise, the few threads you have in Netty or even Node.js, Node.js is famous for the fun Reddit post about try reading a file within a Node.js request. Well, this kind of issues, if you start blocking in the application logic, they really translate quickly in non-blocking runtime environment. So what can we do at the application level?
So you heard it, Rick and Morty. Is that on Netflix?
Yeah.
Okay, that's the prime recommendation.
Prime recommendation, indeed.
So if we turn, actually, I should mention that with Tomcat and Jetty, there's also an event loop in processing the I/O. It's just that at the servlet container and the servlet API model, that's not really what we do. We process on a different concurrency model above. But the event loop implies that there's very few threads being used, a very small number of worker threads. So as Stephane said, what that means for applications is that if we do things the same way, now we really have to change the way we think about things, because we can't introduce any kind of latency or any kind of blocking. And I always like to compare to Node.js, because I think that really puts it in very good perspective to think for a second how you would approach writing server-side applications if there was such a constraint where you only have a single thread. You cannot block that thread, because if you block that thread, then everything is, the world stops. So our applications also have to change, and they have to become asynchronous and non-blocking. And if you do that, then you might find yourself very soon with code that looks like this, and these are the steps to boil rice. It's an algorithm we all have to write very frequently, I know, but it illustrates the point that, I mean, if you imagine really having a chef in a restaurant, you have a single chef, and they have to prepare some food, and while the water is boiling, you don't want them to sit and wait for the water to finish boiling, or you're going to have very hungry and very angry, eventually, customers. So you add a callback. When the water is done, then you're going to proceed with the next steps. And as you begin to get into that mindset, everything becomes a callback. And pretty soon you find yourself nested many levels down. And of course, you've probably heard there are many terms for this. Callback hell, the pyramid of doom, and so on. And we really don't want to be there. We want, in order to achieve a kind of Zen dealing with callbacks, we need to rise above the level of the callbacks. Fundamentally, there are still callbacks underneath, but we want to be on a higher level, more declarative and functional style API that's going to make our code readable again, just like it was with the imperative style programming. But fundamentally asynchronous, and the code becomes neutral with regards to whether something is being done synchronously or asynchronously. I want to stress that synchronous doesn't mean bad. In fact, synchronous is faster than asynchronous because you have to do more things. But we want our code to be sort of independent of whether things are being done synchronously or asynchronously. Can we get some help from the JDK? In fact, in Java 8, we do have facilities. We have the completion stage and completion feature that give us the ability to not only perform something asynchronously and get the result, but we also get a notification back. And then, in addition to that, we can attach actions to these notifications, and we can compose asynchronous logic, which, in combination with lambdas in Java 8, actually makes the code pretty nice and readable. In Java 8, we also have the Stream API, and that allows us to perform a variety of operations on sequences of data. We can apply operators like map and merge and flat map, and again, with lambda expressions is the same effect, except this time we're talking about a sequence of data. The challenge with Stream and the Stream API is that it's really built for collections, for arrays and collections. Where what we need, and this is going to be the subject of my next talk after the keynote, where I'm going to go into more detail into that. But with the Stream API, what we actually need is to deal with latency. We want to make an asynchronous call, and then the data may come back immediately, or it may take a few seconds. We really don't want to block. We want a kind of a push-based model, whereas with the Stream API, it's a pull-based model, which means that it's really not suited for any kind of latency-sensitive scenario. This is why we turn to reactive libraries like Reactor. And Reactor provides us with an API. It's a little difficult coming up with names in a space where you must stay short, and there are already so many. But we think we've done well with Flux and Mono. So Flux, you can think of it as the equivalent of the Java 8 stream, and that gives you a stream-like API to start. But it's one which can deal with any sequence of data, not only arrays and collections. In fact, arrays and collections, and it's easy to convert from Java 8 stream to Flux. But you can also deal with latency-sensitive scenarios, and there's a lot that comes with that territory, and that's really what reactive libraries deal with. Mono is similar to Flux, but it's specifically modeling the case where you have a sequence of only one element. And that's a very common scenario in APIs, and it makes a lot of sense to have that represented explicitly. And by the way, these are marble diagrams. I guess once you start looking at things like that, they're very, very useful. You can see the sequence on top, and then there's an operator of some kind which applies some transformation, and then you have a new sequence underneath. And then these red X's, that's when that's a termination signal when the sequence is finished, because these could be infinite sequences as well. Now, Reactor is a very collaborative effort. As we mentioned earlier, the Spring Framework team has been working with the Reactor team over the past year, trying to align in the sense that we kind of did our R&D, then we set about building what we wanted to build, which is a web framework, and again, we'll talk about that in a little bit. And in the process of doing that, we basically kept communicating and saying, well, this is what we need, and he would say, well, this is what we have, and then we just kept going through questions and answers. We went through many phases, and again, today we have Reactor 2.5. Is really a tremendous amount of momentum behind the Reactor project at the moment. And also, that sort of momentum tends to attract other positive efforts. So, for example, we have essentially the lead committer from RxJava taking interest in making steps towards becoming kind of a library or a shared library with Reactive Streams infrastructure, and that's the Reactive Streams Commons project, which is a kind of shared project that may be used in RxJava too, maybe. We don't know yet, but certainly it's extremely helpful for us in Reactor also to have the participation of lead RxJava committer. And Reactor also has an I/O module, which means that it gives you a Reactive Streams abstraction on top of runtimes like Netty. Now, in addition to having a really nice composition API like the Java 8 stream and being able to deal with latency-sensitive sequences, again, I said that's a territory that comes with quite a few challenges when you have latency-sensitive scenarios. Well, Reactor also deals with the concept of back pressure, and that's really what the Reactive Stream spec is all about. It's an industry collaboration specification. A number of companies came together and created this really small spec. It's only 4 interfaces, and the 2 main ones are right here, publisher and subscriber. They just have like really just a few methods. So a very simple concept, and publisher and subscriber is not what they invented. That's been around for a long time. What is completely novel in this specification is reversing the relationship between publisher and subscriber. So the publisher is still responsible for pushing data, but the subscriber, you can think of it as a volume dial. You can say, I want more data or I want less data. And if the dial is on 0, the publisher is not supposed to publish anything. And this is extremely important as you begin to deal with these kinds of consumer-producer scenarios, event-driven style applications, because it allows a mechanism where we can slow things down and the publisher is not allowed to send things down. And I'm sure that brings a lot of questions. You may be wondering, how can that apply to my situation? Publisher has to publish. There's no way. They can't wait. So we'll talk about that in a moment as well. But just think of the concept. I mean, that's the idea, is that you have a mechanism through which you can not only fill up the thread pool, which is our primary mechanism today, but you can push back to the source. And if that source can slow down, they will slow down. And if they can't slow down, well, at least they know that we're not able to process. So at the end of the day, we have to work something out. But the important thing is that there is a mechanism through which this happens. And of course, I do want to emphasize that Reactor is an implementation of this, so you automatically get Reactive Streams support and integration. Flux and Mono are implementations of Publisher, so you automatically get that benefit as well. So given these tools, let's talk about how would we scale with all that.
So if you remember, we talked about non-blocking runtime. Now we have a solution for non-blocking applications. Of course, Reactor is not the only one available to deal with asynchronicity in the application layer. But the point is, with this volume control, Rossen just discussed, we have interesting new possibilities, but also new challenges. So what does it mean in terms of scaling in a classic situation, especially in the microservices architecture situation? you will recognize this kind of scenario, even if the Y is just below the gateway. So gateway is in yellow on the left, and you recognize this kind of situation where you kind of connect with a backend. The gateway can be also a load balancer, whatever, but the service is your application, and this application can connect to, as I said earlier, to a remote database, a remote other application through HTTP, or a remote message broker, and consume message pushed by the message broker. So if you think about what happened now with flow control, as defined by the specification by Reactive Streams, all these components you see in service A, there are actually a few components, the Spring logo actually, which could be decorating or using a publisher as a contract. So that means they could have this volume control enabled. And the volume control is interesting because what really happens, in a system when you have a back pressure you control or you don't control, that's interesting because in some situation you will be able to, like the arrows, like it sounds like you will be able to see that as a kind of proton-electron mechanism where things can push back, can pull. That's interesting because sometimes your application will be, some components of your application will be on demand, so asking for more data, attracting more data. And sometimes it will be in a situation where you want to push back, so not requesting anymore, and pushing back the data to the source. So that's really the kind of mechanism we are talking about. And the problem or the challenges you have is there are no similar source of data. They have different patterns. They're a bit by different rules. The data store, for instance, is what we call a cold data source or a cold source because we can connect to it anytime, pause, resume. We can slow it down, basically. So the volume control is effective here because if we turn the volume control to 0, it's fine. At some point, any time later, because the data is persistent in the data store, you can use the volume control again, ask for data, and the data is still here. We also say that it's a replayable data source. So for data store, it's interesting because back pressure in that case, the request, the volume control will directly translate in volume. So for instance, you can limit the number of rows you read from the database. If you have a request in back pressure terms, in reactive stream terms of 32, you can translate that into 32 user you read from a database, for instance. And you can do pagination, for instance, like that. Even if the connection to the database itself might be blocking, and that's another challenge. There is a few, at this moment, there are only a few non-blocking drivers to databases. But if your database, at least, and if you consider the access to the database as a kind of paginated request, you can quickly translate the volume control into the number of rows you read. Also, you have a different situation, completely opposite of the database scenario, where actually you've been pushed by a message broker, classic scenario where RabbitMQ Kafka pushes messages to your application as quick as it can. And these are often, event-driven, well, they are event-driven, but they're often user-driven events, trades, UI events, click, etc. Things that you have to accept at all costs from the application perspective. So the reactive stream specification is not really going to help in that scenario. That's an issue. But the reactive API you use might help you because what do you do if you didn't ask for a given amount of data? And remember, this thing is going to push to you application regardless of the volume control. The volume control has no effect on the message broker in that case. Well, it could, but right now, if you want to accept all events, because you consider all events important, you have to accept all these events. So in that scenario, you will have to actively deal with the back pressure, the overflow. You can't slow down the number of events coming from the message broker, the event coming from an outsource. So in that scenario, you will actively drop, maybe buffer temporarily, but you have a control. You have to explicitly control how this is going to happen, and that's a challenge. And then you have a mixed situation when you connect through HTTP, for instance. It's not a cold source because the service is maybe replying idempotent result, but still it can be asynchronous and it can come anytime later. And the service B can be requested for data. So as a service A, you say I want some data, And whenever the service B is ready, it's going to say, OK, send me your data. And then the opposite situation actually happens, because as a service, an HTTP service, for instance, you have to reply at some point. But maybe the service A is not ready anymore at this time. So the back pressure works both ways. You can reply fast enough, maybe because the situation of service A, but also you cannot send if the service B hasn't requested data. So the back pressure can be applied to various end-to-end scenarios in distributed system. And in the end, what we do is not rocket science. It has been in network, in routers, for instance, network components for a long time, even in systems for a long time. This volume control, this technology in the JVM now is like a quality of service. You can define how much your application can accept at a given time. And if you think about the full picture, if you control how much your application actually consumes, you can predict its load, you can predict how many instances of your application you might need, and that's very important. That's really the quality we want to define with reactive system. It's not about speed, it's about stability, efficiency, and reusing the maximum of the resources you have in place. So there, if you think about that as well, you think that I presented a few icons where there were Spring-related components, and I mentioned the term end-to-end. This is important to think also. The fact that you need to change as a domino effect through all the application logic. All your components start being reactive or need to be reactive to properly propagate the back pressure, except even in the situation of the message broker outsource where you need to drop. You need to be aware of these kind of scenarios and back pressure end-to-end. Otherwise, if you break it, that doesn't work. It only works if you have really the source of your data connected to the consumer of your data. If you break that contract, it doesn't work. So you need an ecosystem. So what do we do now? How do we deal with that, Rossen?
So what does all this mean for Spring and Spring applications? So we've been working over the past year, and I'm going to share what direction some of that has taken. But one of the key decisions in what we did, and again, when we started a year and a half ago, the landscape was completely different. It was before Reactive Streams was final. RxJava was just becoming 1.0. A lot of things have happened since, but we went through quite an evolution process in the thinking through many phases. And one of the key decisions that I want to take a little bit of time to explain is our choice to use the Reactor project not only as a core dependency in a Spring Framework, but also to expose it in our APIs. Because this may seem contradictory to the kind of the Spring philosophy of allowing choice. And we really started out from a very different place where we said, we're going to do what was the prevailing wisdom of the day, which is to expose only Reactive Streams contracts like publisher, subscriber in our APIs. And when I say APIs, I mean things like web framework contracts, places where there is asynchronicity and we need to model those scenarios using asynchronous non-blocking input or output values. So the prevailing wisdom was just expose publisher subscriber, Reactive Streams, and then the application can use any reactive library and can do composition. Now, the first thing we realize is that if you start implementing Reactive Streams contracts, you end up with callback hell. And that's not really the fault of Reactive Streams. That's not really its purpose. Its purpose is to kind of define the relationship between components. So we realized very quickly that we need an implementation of Reactive Streams in order to have some infrastructure around it. It really isn't something you want to build from scratch. It seems easy at first, but it's really non-trivial to deal with these kinds of scenarios. So then we said, OK, we're going to use a subset of Reactor because we don't want to use all of Reactor because then that would be different reactive libraries in the application. And Reactor would be used for infrastructure, but then as we began to write our logic, we found ourselves using operators and more of Reactor. At first, it was just a few operators like map, concat, merge. And then pretty soon, we were dealing with error handling, with default values, and all sorts of things. And after all, building a web framework is very much like building an application, because these are the things that the application would otherwise do. So eventually we realized at the conclusion that we needed all of Reactor, and that was a moment that simplified a lot of things that had been accumulating. And today we have Reactor and Flux and Mono exposed in our APIs. They're infinitely more friendly than the Reactive Streams types. They allow you to do things instantly. We think that's an approach that's working out really well, and it feels like the right approach. And at the same time, it doesn't prevent us from supporting any reactive library. RxJava is a first-class citizen in web applications. This is something we always do, kind of adapting to whatever the Spring MVC or web application is using. So what does it mean for Spring MVC applications? Well, it turns out that the annotation-based programming model, the controller-style request mapping methods, are still all right. There's nothing fundamentally blocking or synchronous about that model. The method signatures are flexible. We can adapt to different type of scenarios. So basically, in what we're building today, the same annotations that you have from Spring MVC, we're still working with those annotations. And in many cases, you'll be able to take an existing controller and just run it in this new way of doing things. Now, underneath that, however, is where all the interesting change needs to happen. Replace interesting with a lot of work. So Spring MVC, all of the internal contracts, everything is built around the servlet API, and there's a lot of synchronous and blocking semantics built into that. So basically, we need to go through the process of taking every contract and thinking, is there latency possible in this contract? And in most cases, the answer is yes. You could imagine various kinds of scenarios, and we need to rewrite those contracts, which basically means we cannot share any code physically with Spring MVC as it is today, but we can replicate a lot of the logic. It has to be all built around new contracts. So if you take the handler mapping, for example, is something, if you're familiar with Spring MVC, you may know. That's the component which takes the incoming request and then gives you back a handler that's going to handle this request. So we still like this contract, but we need to make it asynchronous. So for that, we're going to replace the return value with one that has asynchronous non-blocking semantics. Now, this can give you back a handler or an error through that mono. And we've gone through the process of changing all of the existing contracts, and that allows us to do a lot of things. Like, for example, if you have a request body argument, it means that we can read the entire input from the request. We can deserialize it. We can create the actual object. We can validate it and pass it in. And all of that happens in a completely non-blocking fashion without holding any threads. When the data is available, we read it. If it's a slow client, there is waiting involved, but there is no blocking of threads. And the change goes deeper. What about the servlet API? Well, a lot of the servlet API, we're talking servlets, filters, those are all similar challenges. You have a kind of return values that are blocking and synchronous semantics, and that means that we cannot use the servlet API directly as it is. We actually have to provide alternative means, basically go through the same process for what the servlet API provides as well. In fact, the servlet API has a non-blocking API in servlet 3.1, and that's something that we are taking advantage of. But this is not something that's going to help us with the basic contracts of servlet and filter. And we can ask similar questions down to the servlet container. What is our runtime in this environment, in this context? Can we still use Tomcat and Jetty? So the answer is yes. We can still use Tomcat and Jetty. We can still use Servlet 3.1 containers because, as I mentioned, Servlet 3.1 has a non-blocking API, and we can translate that to reactive streams, back pressure. If the input that's coming in is not available, then we slow down and we can accelerate. So all of that can be translated, and we can create a bridge to reactive streams. In fact, we've already done that. There is no official reactive streams Servlet 3.1 bridge. There was some discussion for that to be in Servlet 4, but at this point it's looking less and less likely with each day passing by. But in any case, we have built that. We're not waiting for that. In the meantime, we're also interested in any non-blocking runtime. Netty is an obvious choice. We're also supporting Undertow at the moment. So this really opens out some interesting possibilities that you no longer have to be necessarily constricted to the choices that we've had for a long time. But if that's what you have today, this is what we provide. And this is actually, I believe, something unique. We're doing a lot of things here from the perspective of Spring applications and enterprise applications that we think, even though there's a lot of efforts out there in the reactive space, we think we're doing a lot of things that are unique, for example, by targeting all of these runtimes. I don't think there's anybody out there doing that. I think a lot of the solutions are targeting Netty, moving on, not necessarily looking back. We're really trying to maintain kind of multiple levels here, different approaches in parallel, because that's what makes sense. So this is the full picture of what we have today. At the bottom is the runtimes that we support. Again, we have a repository with integration tests. We have samples that are actually running. This isn't something we're planning to do. This is something which is work in progress, and in just a couple of weeks, it will be in master branch of the Spring Framework, and then in a couple of months, it's going to be a milestone, a first milestone. Above the runtimes that we support, you have an HTTP Reactive Streams layer. This is where we translate Reactive Streams semantics to the HTTP runtime. So in the case of Tomcat and Jetty, we have a Servlet 3.1 to Reactive Streams bridge. In the case of Netty, we have Reactor IO and RxNetty that gives us the same shared HTTP contracts that are based on Reactive Streams. And for Undertow, we have also our own bridge that we've created because there isn't one that exists. And then above that is the Spring Web reactive layer that's going to be there together with Spring MVC, supporting the same programming model at the top with the annotated controllers. And you can see that at the application level, we plan to support any reactive library. RxJava is a first-class citizen. Reactor, of course, because that's our core dependency to begin with. And at the moment, all of this work is in a GitHub repository called Spring Reactive. This was originally an R&D effort that eventually became, well, it is the base, what's going to be merged into the master branch very soon. So that's where things are at the moment, but pretty soon they will be in master in Spring Framework. In addition to that, we're also working on applications that are, or sample applications that involve kind of more of a full stack approach, not just a web layer. Of course, the web layer is the place to start, but beyond that, there are many questions about how we will retrieve data. And you may be wondering, you know, if I'm using blocking drivers and there's nothing else available, well, there is a way to make that work. So it's not a chicken and an egg situation where everything must become non-blocking before you can do any of this. That's not the case. But there are examples of non-blocking libraries, like, for example, MongoDB has a Reactive Streams driver. Couchbase has a reactive driver. And most recently, we've been collaborating with TimeLeaf on exploring options for kind of a reactive-friendly style of templating. There are some interesting examples in tests already. We're taking a large stream of data and kind of formatting each one of those into HTML, much like we would do with JSON, for example. The same kind of streaming approaches can be applied there as well. And again, that's work in progress, which is already out there. And TimeLeaf 3 has already a foundation for doing this. So these are real efforts that are starting to take place, and you can expect to see more of that. And this is a diagram that shows a couple of different things with TimeLeaf. One of them is where you have a model that's fully resolved with all the data, and then we're outputting one at a time with back pressure, one buffer at a time. And then on the right is where there's actually a publisher that's giving you items, and as they arrive, they're being formatted as HTML and output. Again, these are experiments, but I wanted to highlight them because they show that this is real and this is being done at the moment. There are also Spring reactive efforts that you can expect to see across the Spring portfolio. There are many projects that have already started this effort. Of course, the Spring Framework 5 is there to provide a foundation, and our work with the Reactor project has opened up a lot of possibilities for the other teams to also start moving in this direction. There are concrete efforts in early stages in Boot, in Spring Security, Spring Data, Spring Cloud, and Spring Integration. So you can expect to see all that, and hopefully when we come back here next year, we'll have a very complete story. But even this year, we have plenty of exciting things to bring. So thank you very much. We have more sessions on this today, and if you have any questions, we'll be around. Thank you.
Thank you.